So let's take a look at PTC Integrity Modeler. The first thing to note is that Modeler runs live on an underlying database. And here we can see that we have two databases which are running and available for use. Inside these databases we can then have our models, and here we can see some example models and the models that I'll be working on during this session. This underlying database means that we can have multi-user access with many designers accessing and updating models at the same time from many different locations. This means it's ideally scalable to large teams working together concurrently on designs. So let's take a look at an example model. Inside this model, we can firstly see the general structure of the data. This is made up of diagrams, so here we have a collection of diagrams, and then the underlying data that's shown on those diagrams. This is an important separation. Let's create a new diagram and see how this works. So I'll create a new block definition diagram. We'll describe the diagrams in a bit more detail later and just put a few items on it so that we can understand them and see how this works. So I'll put a couple of blocks on the diagram. At the same time, this is creating those items in the underlying database. So here are those two items. I can also put them on other diagrams. So if I create another diagram, which is blank, and include those same two blocks that we used earlier, I can represent this underlying database of information in different views. I can then do things like change the name, and that's immediately changed in the underlying database, so we can see the new name for our block down here, and it's also changed on all the diagrams that use that underlying item. So this is a first important concept inside a model, in that we're getting consistency across all of our diagrams through the single source of underlying data. This is a great improvement over tools like PowerPoint, where you'd have to go through and update every slide when you make a change to a graphic. So let's go back and start to look at this model in a bit more detail. In this example, let's look at designing a truck at the systems level. I've got started already with my truck, and I want to consider its context in its wider environment, so the truck domain. I'm looking at the stakeholders, the actors involved with my system, with my truck, so I have a driver, and the other systems that it interacts with, so the load, the fuel that it uses, the environment in which it runs. And this helps me with my system design because it lets me understand the other systems I need to interact with and their constraints, and the people, the actors, the other systems that use and interact with my truck, so the driver. In this situation, I noticed that I've missed out an actor that's important, so let me add in a mechanic who can repair my truck when things go wrong. This is the default graphic. Let's make that look a bit nicer. So we now have a mechanic involved in our system, and I can link that up to my domain to say that this is part of my super system, so this mechanic's involved. So it's a great way of workshopping, brainstorming, understanding your environment, and working out how your system, in this case the truck, is going to interact with your stakeholders and users, and also the other systems that interact with it and the constraints that they apply to your system design. Now that we know who our stakeholders are, we can discuss the requirements with them and describe those using a requirements diagram. These requirements can be created directly here in the requirements diagram, or they can be brought in from other requirements engineering tools such as PTC Integrity Lifecycle Manager. And those linked requirements I can pull straight onto diagrams just like this. So here we can again brainstorm, understand the requirements, link them together, show the nesting, and really clarify the underlying requirements of my system. In this example, we've got the truck which is capable of carrying loads. The driver should be allowed to drive the truck. The vehicle shall provide a sleeping area, and you should be able to refuel the truck. But this is a great way of seeing if you have missing requirements, so that you're sure that you get all the information you need. And these requirements can then have detailed text, just as you would with any detailed requirement or story in a requirements engineering tool. Then, to start to define and refine this design based on the requirements, we can drill down into use case modeling, which is again a standard SysML approach. This has the advantage of moving from many hundreds or thousands of requirements into the general services provided by our system. So generally you'll have many requirements being refined into single use cases, so services provided by our system. In this example, we can see that we have our driver who's involved in operating our truck. We also have the ability to load, unload, drive, sleep and repair our truck. Again, I have that missing actor, so I could bring in the mechanic now and link it up with this repair item here. So let's link him up, and again we could make this look good. Another key benefit of this use case modeling is that it's very easy for stakeholders to understand. They can see themselves in the design and the roles that they play and the features and services provided by the system that they're going to be able to use. So the driver can see that he's able to sleep, drive, unload and load the truck, and the mechanic can see that he's involved in truck repair. As with all model items, use cases can also have descriptive information. Let's take a quick look at the description for this use case, operate truck. So the driver is operating the truck, which includes loading, driving, sleeping and unloading. That said, this is the typical way of use case modeling and defining use cases, but these descriptions can be ambiguous. So a great way to define that in more detail and less ambiguously is to define it in a sequence diagram. What we do is take each of those parts of our use case description for operate truck and represent them here as steps in an ambiguous version of our use case description. And then for each of the items in this description, the nouns, we represent those as vertical lines. So we've seen the driver already, but the driver in this case loads the load bay. So we need a load bay, and we need a part of the cab for driving from, a part of the cab from sleeping from, so driving and sleeping. So we represent the structural parts of our system as these vertical lines. Then we go through our description of our use case again and identify the activities, the functions, the things that are happening, and represent those as interactions between these vertical lines. So in this case the driver loads the load bay, and that represents this item here. It's very simple and easy to add items in, so maybe we'd like to park the truck. Like that, and that's an interaction that we can now add between the driver using the cab to park the truck, and we can give that a name of park. So it's very easy to take the description, extend it so that you can really clearly define this use case in more detail. But what it naturally does is allow us to design in a structured way the structural parts of our system, so we know that every noun over here is becoming a structural part, and also identify all the activities to represent the functions of our system. So really we have requirements, functions and logical structure. This means that if a requirement changes, just as we added in parking the truck, we can see that we have a missing function that we need to add into our design. If we have a piece of system in our architecture over here on the right that's not connected up, then we're designing something that's not needed by our system. If we have a change either over here to our architectural design of parts of our system, or even the functions that have an impact on the requirements, we can see that directly through this traceable link from our structure to our functions to our requirements. So this takes away the magic step of jumping from requirements to functional architecture. It gives us a logical, progressive way to iterate through our design and create a structure based on requirements. It also automatically gives us traceable links from our system architecture, our functional architecture, back to requirements. So once we've created our structural blocks, as well as viewing them here in this interaction, we can see them in a structural view, such as an internal block diagram. And here we can see all of the blocks with their ports and connections. At this stage, we're now ready to allocate functions to blocks if we haven't already done that through sequence diagram. So we have an allocation option for activities or functions onto blocks. Normally these would already be aligned using the sequence diagrams. But then we can also allocate the various different domain disciplines to our different engineering groups. So in this example, the sleeper cab has a mechanical subsystem, which we then pass off to be designed using CAD approaches and engineered using standard mechanical engineering techniques. But on the left, we also have software which runs on the sleeper cab in the ECU. And this software subsystem can be allocated across to another design environment, and we'd recommend UML. And in fact, you can use PTC Integrity Modeler for UML to model and design software and automatically generate the source code. So we can provide end-to-end traceability all the way from the source code up through the software design and back through the system design, all the way up through to requirements. Coming down, we're also allocating the sets of requirements to these subsystems, which are allocated to mechanical, electrical, hydraulic, pneumatic, software engineering disciplines. This is a great place then to hand over for the more detailed design and engineering. In this simple demonstration, we've shown a top to bottom flow of design. In reality, you may start middle out or even bottom up. But top-down is a good flow to understand how the various diagrams link together. Information would be gathered as we go, and as we find new information, we'd iterate around our design and add information at higher levels or at lower levels to flow in both directions. But when we get to this stage, we may then want to try and understand the overall trade-off analysis between our subsystems. In this case, our truck's made up of a sleeper cab with a load bay, 2 load axles and a driver axle and a chassis. We can allocate values to all of these parts in our system. So if we look at our blocks here, we can see that we have for our chassis, we have a mass, and we have a little editor that we can use to define an estimate of the weight for that part, the margin, and the budget if it's made of other parts. So by setting the values for each of these individual parts, we can sum the total weight of our truck and see whether it's in the boundaries of our requirement. So we provide budget reporting, which runs on top of the model and understands this aggregation and to show the parts that are built up and their weights, and gives us a total. And here we can see that our total weight of all the parts is 320 and our budget is set for 400. Of course, if the requirement was for a smaller weight for our overall truck, let's see what happens if we change the overall mass budget. So we'll bring that down to 300 and run our budget report again. And we'll see the numbers have turned red and we're now overweight based on the requirement. So this is a simple example showing weight. This could be cost, power consumption, any other variables, to give us a good detail of trade study analysis to understand which are the best options for our parts of our system. One alternative to this budget reporting is also system simulation with an add-on tool called SciSim, and that's provided in a separate video. While we've been modeling and adding these associations, these lines and arrows between our various blocks of our system, we've also been creating underlying traceable links. One example here is that I can report on the usage of this item. So this is the load bay, and I can see that that's been used in this sequence diagram, or in other words, in this use case. So I can open up that use case. So here's the familiar use case, and indeed here's our load bay, which is involved in this scenario. And from here I can then just right click and show this use case in the relationships browser view. So here you'll see all the links and relationships between the parts in our model. For this use case, we can then see what it depends on, and here we have all of the requirements this use case implements or satisfies. So we can trace all the way back from the blocks, the subsystems, the parts of our system, indeed the functions as well, all the way back up to the use cases, through these sequence diagrams, and back to the requirements. So we have full end-to-end traceability. And we can also drill down through requirements as well and find the use cases that are implementing those requirements, and then drill down through the use cases to the parts and the subsystems. So we have full end-to-end traceability, both top-down and bottom-up. At any stage during our design, we can automatically review our model using PTC Integrity Modeler Reviewer. This provides a full set of reviews out of the box, 110 plus, that you can turn on and off and configure to automatically review the completeness and correctness of your design. The first result is a management dashboard showing you the percentage that's complete and correct, and the failures, in this case 72 and 28%. Each of the items that has failed is identified in the list, and at the bottom we also have a prioritized list based on the number of problems found. So we can jump straight to those and see here are the use cases not scoped to an increment. If we don't know or understand that problem, we can pop up the help, which shows us a description of the problem, the consequences of not fixing it, and the strategy for fixing that problem. This is us good mentoring on the job, and helps people who are infrequent users or new to modeling understand what to do and how to do it, and improve their designs over time. As well as the ability to understand the problem, we can fix it automatically. We can choose to ignore it and flag that to a manager or review panel. We can add a comment, and we can jump to the item directly in the model, and that will open up Modeler on the problem so we can go and directly fix it. So PTC Integrity Modeler Reviewer gives us a fantastic set of out-of-the-box reviews for completeness, correctness and metrics, but also provides active mentoring on the job to help users improve their designs over time. Once we're happy with our design, as well as providing live access onto the model, we may also want to publish it into tools like Microsoft Word or HTML so that we can publish it on our intranet site. To achieve this, we use the PTC Integrity Modeler Publisher, and we can use predefined templates or define our own definitions of documents that we want to generate. Choose the output format, and it will automatically generate our documents for us. In this example, it's generated me a PTC template based document with a nice title page, with a table of contents, with a table of all the diagrams, all of the figures, and then further down all of the information, and the diagrams and pictures that we've seen during this demonstration nicely formatted and placed into our Word document, along with all the detailed information below those designs. So it's a very quick and easy way to generate out graphics, dictionary data information from our models to publish to people who maybe don't have access to the modeling tool or not familiar with using it. Now let's take a look at model-based product line engineering in PTC Integrity Modeler. In addition to the underlying 150% models, and here's our truck again, which has a day cab and a sleeper cab, so it's an overloaded 150% model, we can also model the variability using a variant diagram. So here's an example, and we're showing a variation point of accommodation, so you can choose whether it's a city truck or an overnight truck. And based on those marketing decisions or business decisions, customer options, it will then select between the two underlying base items from our system model, sleeper truck and day cab. This is truly orthogonal. You can model any variability you choose. So we have fuel types, length of chassis, and use this to drive the decision-making process on top of your 150% overloaded or family model. So that's stage one, is variability modeling. Once we've designed our detailed variation, we then want to make decisions based on the options. So here you can see that we can choose one of the options, either city truck or overnighter, and we have to choose one, and we can only choose one. So we do this with decision sets, and you can create any number of decision sets, and they look like this, and you can edit them to make decisions about what option to include. So here we can include a city truck or an overnighter. As well as this internal format, which is good for debugging and editing variation trees, we can also use a web interface which is more appropriate for customers, marketing, maybe management. And we can see here the options again for our city truck, and it's got the same choices we made in the other view. So I can turn off city and say that we'll have an overnight truck. So there's two options for making the decisions and choosing between the options and variants. So that's stage two completed. So now that we've made our decisions, either using this web-based variant selector or the integrated decision set editor, which will both run on top of the variant design in our model, so the variations, and the underlying system model, so this is our overloaded or family system model, we can automatically generate the product model for those three inputs. This creates a new model linked back to the original and resolves all of our decisions for the product line decision set. This is a unique facility provided in PTC Integrity Modeler and is detailed in another video in more depth. This is a high-level summary. So let's go back and look at our truck, and you'll see now that we don't have the day cab, we only have the sleeper cab. And from here we could run budget reporting or simulation and make new decisions and generate new product instances. So that's a quick summary of the model-based product line engineering in PTC Integrity Modeler. Now let's take a look at simple asset-based modular design. In a separate model, I've modeled a drive axle made up of various parts, and the axle has three different interfaces that it provides that you can use to connect with the rest of your system. I could include the requirements that this subsystem implements and the use cases. I could also have variation points on this item. In this simple example, I'm just defining some interfaces. To publish this drive axle into PTC Integrity Asset Library, all I need to do is make it an asset, And then you'll notice here that in the browsers I have a browser directly into the asset library database. So this is a separate database outside of the modeling environment. I can view that database over here through the asset library web browser interface, and we can see in here that there's just a load axle and an example. So it's a simple case of just dragging and dropping from my model environment into my asset catalog. It will ask me for a version, and this I would normally use the version of the model, and publish the asset for me automatically. I can now see that asset. If I move over and refresh the screen, I can see my drive axle with its design and its interfaces published from the modeling environment. So that's stage one, designing a low-level asset and publishing it. Published assets are stored in the standard OMG reusable asset specification database structure, so these are all documented that way. This means that I can define information about those assets, so I can say how long they take to build and how long they take to reuse. This is very useful when I'm working out the return on investment from reusing assets in my management dashboard within Asset Library. I have a full catalog here, and I can publish as many as I need, either from models or from parsing source code if I'm looking at assets for software, or just any type of asset that I want to document in the Asset Library. If I don't navigate through, I can also use the search facility to go and find an asset that I may want to use. It also provides the standard keywords and states that come with the OMG reusable asset specification. And as there are a number, I can just identify them, and it will move around in the asset view and change the view to show me them, and I can decide which one I want. It's panning around and showing me so I can find them. So I can quite easily publish, and then I can find assets that I want to reuse in my design. If there's nothing there at the moment, I could look at a catalog or maybe even an asset that's not quite right, and I can raise this flag which shows I'm interested, and when new versions of those assets or new assets are published into the catalog, I'm automatically emailed so that I can see those assets and choose if I want to use them now. Now that I've found the asset I'd like to use in my design, I can bring up the Asset Library browser in the modeling environment and use this as a palette to design from reusable parts and use them in my own design environment. It will ask me how I want to map it, so I'll map to SysML because I'm modeling systems here. So as we see, we now have the drive axle that's come in. If we look in the property pages, we can see that it's pointing back to its master asset library and the ID of the asset, and in fact its version, which is also shown on the diagram. This now means that we have the drive axle in our database, so I can use that on my models. So if I bring in my drive axle, I can add it in the interface, the drive input, as a port. So let's make that a port, and then I can link up this drive axle using a connector from my chassis to the axle. So as you can see, very simple publishing of reusable assets from one model, and then using them in another model and connecting them up to build a system of systems from a palette of parts. These reused parts, I can also navigate and go back and find the asset in the asset library, so it'll focus asset library for me and go and find that asset. So if I want to go and read the information about who created it and when, that's all available. I can also map from this asset and open up the other model, which has got the details, the internal white box details for that other asset in another copy of PTC Integrity Modeler. If we can then take a look at the internal design for the asset that we've been using. So that gives us full Modular design. We've looked at an approach that was a kind of bottom-up mining of assets and publishing them. As well as that, we can also see a top-down approach of modeling from a conceptual design of parts that maybe I want built by different teams or different organizations, and I can allocate out these parts to be designed by different teams, give them contracts through Asset Library so that they can do exactly what we've seen. They can bring in the contract with the interfaces, design all the internals, and then publish a completed asset for use in this super system level of modeling. So that's a quick introduction to asset-based modular design with PTC Integrity Modeler.